So in this video lecture we'll be solving another numerical of limit state method, and this is the same numerical type 1 that we had solved previously. So what is given here is RC beam, reinforced concrete beam of width 250 and 550 mm effective. Now this word effective is important. So this depth which is given is effective depth, is reinforced with 3 bars of 25 mm diameter on tension side. So AST is given, area of steel on tension side, using M20 grade of concrete is given and Fe 500 grade of steel is given. Beam is simply supported for a span of 8 meters. Determine the safe superimposed UDL, and effective cover is 50 mm. So this is the same kind of numerical that we had solved previously. Width is 250 mm, effective depth is 550 mm. Along with the normal solving that we had solved in the last numerical, we will be solving a bit more in this, and we'll go into a bit more concept into this numerical. Effective cover is 50 mm. So what should be the total depth? It will be 550 plus 50, right? Total depth will be 600 mm. Span is 8 meters. FCK is 20 megapascals. Fy is 500 megapascals. Number of bars 3 and dia is 25. So area of steel will be 3 into pi by 4 into 25 square. Correct? So it is 1472.6216 mm square. Now step 1 is to find actual neutral axis, and we know how to find actual neutral axis. It is by equating compressor force to tension force. So C is equal to T. 0.36 FCK BXU is equal to 0.87 Fy AST. We find XU, and here it will be 0.87 into 500 into 1472.6216 divided by 0.36 FCK B 250, right? So XU comes out to be 355.884 mm. After finding XU, we have to compare it with XU max to check whether the section is under reinforced valence or over reinforced. So XU max for Fy 500 is 0.46D. So XU max is 0.46D, which is 0.46 into 550. So this will give you around 253 mm. So what we can see, our XU, actual neutral axis, is greater than our maximum neutral axis. It means our section is over reinforced. Step 3 is to find moment of resistance. So for we do not design over reinforced sections in limit state method. So what do? We will limit this XU to XU max. We will not allow this value, but we will have to take it as 253 mm. So 0.36 FCK B XU D minus 0.42 XU. In place of XU, I will have to put XU max here, and the moment of resistance will come out to be, basically you can also use this formula, 0.133 FCK BD square, which is for Fy 500, and you will get the moment of resistance to be 202.079 kilonewton meters. So this is the moment of resistance, and to find the safe superimposed load. Now again, this length is given as 8 meters. This is a superimposed working load. Just note down these words, very important: working load and ultimate load, because many times you will get confused in that. So W, this is the total load that the beam can carry, total working load basically that the beam can carry. It is composed of imposed load plus self weight, and the ultimate load will be W into 1.5, and from where this 1.5 factor comes, that we had seen in the previous numerical. It is given in the load factor table of IS 456, right? So the bending moment diagram of this is obviously a parabola with the maximum value of WU L square by 8, and we will have to equate our moment of resistance to the maximum bending moment. Moment of resistance value we had got just previously, which is 202.079, and it is equal to WU into 8 square upon 8. You will get the value of WU, that is ultimate load, which is 25.259875 kilonewton per meter. Now, once we find WU, we can find the working load W, that is after finding ultimate load, we can find the working load, which comes out to be 16.8399 kilonewton meter. After finding the working load, safe working load, we can find imposed load if we know self weight. So in the previous lecture I told you how to find self weight. It is just multiplying the cross sectional area of your beam. If this is the beam, then we want the weight in as a UDL, that is the self weight as a UDL. Okay, so to find this way, we just have to find multiply the cross sectional area with the density of concrete. Density of concrete, which is 25 kilonewtons per meter cube, right? You must be knowing this value, 25 kilonewton per meter cube. After finding self weight, we can find W imposed, right, which is W minus W self. So W imposed comes out to be 13.0899 kilonewton meter. What does this mean is that if we impose this value as a W safe W imposed load or a superimposed load, then the section will be a balanced section. It will not become over reinforced. Okay, so the meaning of this is that if we since we limited our actual neutral axis to balanced neutral axis and then we found this load, it means that if I superimpose my beam with this load, then my section will be a balanced section. It won't go into that over reinforced zone. But let us just take a scenario where I want to find how much load can actually my beam carry if I would have designed it as a over reinforced section. It is not permitted in IS 456, but how to design a over reinforced section, that also you should know. So for designing an over reinforced section, we first see its strain diagram. Okay, now we are designing this section as how the XU had come. Okay, and like we are not limiting that XU value to anything. So the XU, but the XU that we found previously, something 334, some value was there, right? I don't remember it exactly. This XU was found when my strain was this, when the strain in steel was this, because we had equated this value, right? 0.36 FCKB XU is equal to 0.87 FY AST. When is this 0.87 FY? The stress in steel is 0.87 Fy when the strain value is this, correct? But for over reinforced sections, we know that the strain value is not this. The strain value is lesser than this for over reinforced section. So it is something epsilon s. It is not equal to this value, but it is a lesser value, which is epsilon s. So this 334, whatever XU was found previously, that is not correct value. The actual neutral axis value we will find now. Let me just erase everything. So this is a wrong value, since this strain occurs when the stress in steel is 0.87 Fy, and since in over reinforced sections the stress in steel does not reach 0.87 Fy, or rather the strain in steel does not reach this value. The strain in concrete reaches 0.0035. So we have some value of epsilon s as the strain in steel, and I want to find XU now. So XU divided by 0.0035 is equal to, I'm taking the similarity of triangles, XU upon 0.0035 is equal to D minus XU. This is D minus XU divided by epsilon s. So epsilon s will be 0.0035 into D minus XU upon XU. For this strain in steel, how to find stress in steel? We have Young's modulus is equal to stress upon strain I know strain in steel, I want to find stress in steel. So sigma S will be, or rather I will write it as Fs, okay? Since we are using F as the symbol, I will write it as Fs. Fs is equal to Young's modulus of steel, which is 2 into 10 raised to 5, into strain in steel, which is this epsilon S. So if I multiply this value by 2 into 10 raised to 5, what I'll get is stress in steel at that point. So Fs is, I think there's one more 0 here, right? 2 into 10 raised to 5. So it comes out to be 700 into d minus xu upon xu. This is the stress in steel for this strain, for the corresponding strain. So the stress diagram will now alter. This is the stress diagram for concrete, but here instead of taking 0.87 Fy, I will take the value of stress which is actually coming there. So my tension force will be now what? Fs into AST, that is stress in steel at that level, which is Fs into area of steel. So again I have to equate C and T. C is equal to T to find actual neutral axis depth. So C is equal to T, 0.36 FCK BXU is equal to Fs into AST. 0.36 into 20 into 250 into XU is equal to Fs. I'll put directly this value, 700 into 550 minus XU upon XU into AST. So the only unknown here is XU, which is your actual neutral axis, which comes out to be 343.7123 mm, correct? And the moment of resistance now. So moment of resistance, I will just put directly this XU value here, and let us find what comes. Moment of resistance will be 250.9627 kilonewton meter, and I am directly skipping the steps and I am directly equating it to WU 8 square by 8, which is WU L square by 8. This is what we do, right, to find the ultimate load. So ultimate load comes out to be 31.3703 kilonewton per meter. Working load will come out to be 20.9136 kilonewton per meter. And self weight will be 0.25 into 0.6 into 25, which is 3.75 kilonewton per meter. This is we already found self weight. So W imposed is W minus W self, correct? W imposed is 17.1636 kilonewton meter. So this is the value, this is the safe, I won't say safe, but this is the superimposed load value that if you put on the beam, your section will become over reinforced. And the limiting value of load, when we limited our neutral axis to XU max, this value is what we found previously, right? So you will not put this value we have just found out, rather I have found out just to show you that how you can do the analysis of over reinforced sections. You won't find it in most of the references. So limiting value of load, this value only has to be put on the beam. But had we designed it as an over reinforced section, we would have been allowed to put a greater load on the beam, correct? So when we put this load, your beam will be balanced section. When you put this load, your beam will be an over reinforced section. So I hope this was clear. So in the next lecture, we'll be learning the design of singly reinforced sections, and those will be type 2 numericals. Till then, take care. Thank you.